This is Calculus 1 video lecture number 16 on exponential growth and decay. Now we're going to revisit a topic that you probably looked at in pre-calculus, but now that we are studying calculus, we're going to look at it through a different lens. So in many situations, quantities grow at a rate that's proportional to their size. This quantity can represent a population of people or of a bacteria culture or many other things, including the infection rate of a disease, for example. And in this case, if y represents the amount at some certain time t, and we know that the rate of change of y is proportional to y, then we can write the following. We can say that dy dt, that's the rate of change of y, is equal to some constant k times y, the amount at time t. So if you remember studying variation a little bit, this k here is our constant of proportionality. And it represents something when we're looking at this kind of a model in particular. Here we have a differential equation. A differential equation is an equation that includes a derivative of a function. And it's called the law of natural growth or decay, depending on the value of k. And the value of k is called the relative growth rate. So let's break down this differential equation a little further. If I wanted to isolate k, I would divide both sides by y. So we'd have 1 over y times dy dt is equal to k. All right. Well, here, dy dt, that's the growth rate. Okay, and remember, y is the population. That's the population. So notice that k is actually equal to the growth rate divided by the population. So that's why we say that k is the relative growth rate. So k is a percentage rate of the growth. So for example, if k is equal to 0.03, then we have a relative growth rate of 3%. Okay, so the actual growth rate, that's dy dt, that's the rate of change of the population with respect to time, but k takes that rate and divides by the amount that you have. Okay, so do we know a function y that would satisfy this differential equation? We sure do. And the solution to this differential equation will always have this form. It's y equals c times e to the kt. Okay, exactly how we come up with this, you can wait until you take more calculus to study, but what we're going to do is just verify that it actually satisfies the differential equation. Okay, let's differentiate this equation. Let's take the derivative with respect to t. Right, we can do this, no big deal. C is just a constant, so bring it down. And then derivative of e to the kt is going to be e to the kt times k by the chain rule. And so notice I'm left with k times c e to the kt. So that's what dy dt equals. But notice, what is c times e to the kt? It's y, is it not? So the derivative is equal to k times the original function. So therefore, we found, or we verified that it's a solution, k times y. Bam. Now notice, if t is equal to 0 at time 0, y is equal to c times e to the 0, which is just c. So c is the initial value. Whatever your starting amount is, your initial population, initial amount of bacteria, whatever it may be. Okay? All right, so what we're going to do is use this equation, this model, to solve some of the following exercises, okay? It's also sometimes referred to as the law of uninhibited growth or uninhibited decay because there's other kinds of growth models as well. All right, first example. A bacteria culture starts with 4,000 bacteria and it triples every half hour. So part A says find an expression for the number of bacteria after t hours. So we're going to start off by using the model y equals CE to the KT. And notice they told me we start with 4,000 bacteria. So right off the bat, I know, okay, C is equal to 4,000. They also tell me that the amount of bacteria triples every half hour and T is being measured in hours. So that means after a half an hour, the amount has tripled. So now I should have 12,000 bacteria. So right now in my model, I know y equals 4,000 e to the KT. All I'm missing at this point is k. I need to find k. And how can I go about finding k? Yeah, you're just going to substitute in 1/2 for t, 12,000 in for y, and then find k. So here we go. We've got 12,000 equals 4,000 e to the k times 1/2. Divide by both sides by 4,000. I have 3 equals e to the k over 2. Let's take the natural log of both sides. So ln of 3 equals k over 2. So k equals 2 ln of 3. So this is approximately 2.1972. Okay. All right, so putting this back into our model, we have y equals 4,000 e to the 2.1972 times t. And we've got an expression for the number of bacteria after t hours. Now, another way you can do this, and it's a little more accurate, but you lose the fact that the model uses base e, is by substituting 2 ln of 3 in for k. So let me show you that. You could write this as, that's good, y equals 4,000 times e to the 2 ln of 3 times t, which is 4,000 times e to the ln of 9, right? Because the 2 is the exponent on 3 as well, times t. And then e raised to the natural log of 9 is just 9. So I could rewrite this model as y equals 4,000 times 9 to the t. So what's the difference? Well, notice here I still have base e. Here now I have base 9. However, I rounded here with k, and there's no rounding in the second one. So it just depends. Do whatever your instructor wants you to do. I don't really particularly care one way or another. Just make sure if you're rounding that you follow the directions regarding the number of decimal places. Okay, either one would be acceptable. Part B, find the number of bacteria after 20 minutes. Okay, so after 20 minutes, remember t is in hours, so that means t would equal 1/3. And all this you're going to be doing in your calculator. So you're going to find y of 1/3. Just show the original setup. You have 4,000 e to the 2.1972 times 1/3, which should give you approximately 8,320 bacteria. Okay, alternatively, if you use the other model, that's fine. Or you would have y equals 4,000 times 9 raised to the 1/3, and you would get also 8,320 bacteria. Okay, good. The last part C says, when will the population reach 20,000? Okay, so part C, When will the population reach 20,000? I'm going to set y equal to 20,000. So that means, and actually, you know what, in this scenario, I want this more precise one with the no rounding up here. 4,000 times 9 raised to the t. It just makes me feel better because I know there's no inaccuracy there. So 20,000 equals 4,000 times 9 to the t. Divide both sides by 4,000, so I have 5 equals 9 to the t. Let's go ahead and take the natural log of both sides. So ln of 5 equals ln of 9 raised to the t. And then we can move t to the front there. So we have ln of 5 equals t times ln of 9. So t equals ln of 5 over ln of 9. That's the exact answer. And then t is being measured in hours. So just go ahead, give a nice decimal approximation. So natural log of 5 divided by natural log of 9. You should have approximately 0.7325 hours. Okay, if you want to multiply it by 60 and give it in minutes, go for it, but the directions didn't specify, so I'll just leave it as is. Okay, very good. Now let's look at one more example. As you've probably seen, similar exponential functions can be used to represent radioactive decay. And in this case, the value of k will turn out to be negative. And the term half-life is used to describe the amount of time that it takes for half of any given amount to decay away. All right, so let's see here. They tell me polonium-210 has a half-life of 140 days. All right, cool. So part A, if a sample has a mass of 200 milligrams, find a formula for the mass that remains after t days. Okay, well, I know it's going to follow the model y equals ce to the kt, and they actually told me c is 200, and the half-life is 140 days. So what does that mean? That means after 140 days, half the original amount will remain. So instead of 200 milligrams, I will have 100 milligrams. All right, so let's see here. So I know y equals 200, the initial amount, times e to the kt. And I need to find k. So I'm going to substitute in 140 for t and 100 for y, just like in the last problem. So I have 100 equals 200e to the kt. Dividing both sides by 200, now we have 1/2 equals e. Oh, excuse me, I need to plug in 140 for t times 140. So e to the 140k, take the natural log of both sides. I have ln of 1/2 equals 140k. So k equals ln of 1/2 over 140. Okay, and this is approximately negative 0.004951. So if I'm going to put this all together in the model here, I get y equals 200 times e to the negative 0.004951 t. Or like in the previous example that I showed you, you can rewrite it with base 1/2, should you choose. Okay, let's look at part B. Part B says find the mass after 100 days. So that means I'm going to substitute in 100 for t. So y of 100 equals 200 times e to the negative 0.004951 times 100. I recommend if you're not going to change the base in the equation so that you're not rounding, just leave this number in your calculator. Don't clear it. Just store it so you can refer to it. And then we're going to round to the nearest milligram anyways. So just confirm you can get about 122 milligrams. Make sure you put your units. Okay, last part C asks, when will the mass be reduced to 10 milligrams? Okay, so they want to know when y will equal 10. So I'm going to set this all equal to 10 equals 200 times e to the negative 0.004951 times t. Dividing both sides by 200, I have 0.05 equals e to the negative 0.004951 t. Let's take the natural log of both sides. So ln of 0.05 equals negative 0.004951 t. So t is equal to ln of 0.05 divided by negative 0.004951, and that's about 605 days. Does that seem reasonable? I mean, yeah, if the half-life's 140 days and we start with 200, it makes sense we're going to need several iterations of the half-life until we get to only 10 milligrams. Okay, so hopefully you're comfortable with those examples. Just keep in mind you're going to use that model y equals c times e to the kt for exponential growth and decay. Now we're going to look at an application that you maybe haven't encountered before, and that is Newton's law of cooling. All right. Now, Newton's law of cooling tells us that the rate of cooling of an object is, again, proportional to the temperature difference between the object and its surroundings, if the difference is not too large. Now, I'm going to show you how to solve these problems and work through them in a slightly different way than the text that we're using and some textbooks use. You can do whatever is comfortable for you. But here's basically what Newton's law of cooling tells us. The temperature of some object at time t, so capital T is temperature, okay? And then the lowercase t is time. And that's equal to T sub s, that's going to be a constant. That's the temperature of the surroundings. And this is proportional to the temperature difference between the object and its surroundings. So we're going to add plus CE to the KT. Why do we do this? Okay. Well, I'm going to let y equal T of t minus T sub s. So basically I'm taking this, subtracting this, setting it equal to y. I know dy dt would equal derivative of capital T, so dt d little t, plus T sub s is just a constant. It's the temperature of its surroundings. And what does Newton say? Well, Newton says that the temperature, the rate of change of temperature with respect to time, is equal to some constant times y, the difference between the temperature of the object and its surroundings. And we know that y has the form c times e to the kt. So that's why T of t minus T sub s is equal to c times e to the kt. And then we just move this over to the other side and end up with T of t, so the temperature at some time t, equals T sub s plus CE to the KT. Okay? Now, the thing to remember is that C, that constant, is equal to T naught minus TS. What is T naught? That's your initial temperature of your object, okay? T sub S is the temperature of the surroundings. I'll remind you that. Okay, so just make sure you remember and apply this formula correctly. It just has one extra term on it, the plus T sub S, basically. Okay, example. A freshly brewed cup of coffee has temperature 95 degrees Celsius in a 20 degrees Celsius room. 5 minutes later, its temperature is 88 degrees Celsius. So part A, find a function that gives the temperature reading after t minutes. Okay, well, let's piece through and see. They tell me that the coffee has a temperature of 95 degrees Celsius. So that's the initial temperature. That's T naught, because that's the temperature of the object. In a 20 degrees Celsius room, so that's T sub S. That's the temperature of the surroundings. So I can find C. Remember, C is T naught minus TS. So that's going to be 95 minus 20, which is 75. Okay, so let's put all this into our model. So we have T of T equals, remember it's T sub S plus CE to the KT. So T of T is going to equal 20 plus 75, we just found C, don't forget, times E raised to the KT. So what do I need to do? I need to find K, just like before. Well, let's see, they gave me some info, didn't they? They said 5 minutes later, the temperature is 88 degrees Celsius. So that means I can plug in 5 for T, little t, and 88 for capital T. So let's do it. So we've got 88 equals 20 plus 75e to the k times 5. So this is going to give me 68 divided by 75 equals e to the 5k. Natural log of both sides, so ln of 68 over 75 equals 5k. So k is equal to ln of 68 over 75 divided by 5. And this is about negative 0.0196. So I'm going to put all that together. And now I have my model. T of t equals 20 plus 75 times e to the negative 0.0196 times lowercase t. Now hopefully you see the importance, if your math teachers ever got on you for writing in all caps. You can't do that because we use capital and lowercase letters to represent different quantities. Okay, part B. What is the temperature reading after 10 minutes? Okay, so I'm going to plug in little t equaling 10, yes? So B, we're going to plug in little t equals 10 after 10 minutes. So capital T of 10 equals 20 plus 75 times e to the negative 0.0196 times 10. And you should get approximately 81.7 degrees Celsius. As far as rounding, just check with your instructor what they want. Check with whatever the back of the book gives. Okay, I'll be specific on an exam how many decimal places I want. Okay, last part C says, when will the temperature reading be 70 degrees Celsius? So this time I'm going to set the function equal to 70. So 70 equals 20 plus 75e to the negative 0.0196 times t. I'm solving for little t. So that means 50 equals 75e to the negative 0.0196 t. Divide both sides by 75. So I have 50 over 75, but that's 2/3 equals e to the negative 0.0196 t. Good. Natural log of both sides, so I have ln of 2/3 equals negative 0.0196 times t. So t equals ln of 2/3 over negative 0.0196. And then this is about 20.7. What were our units for time? Minutes. Okay. So not too bad. As long as you just remember the model, right? For the law of cooling, what the equation's form is, you should be fine. Let's look at one more example. A thermometer in an air-conditioned room reads 70 degrees Fahrenheit. The thermometer is taken outdoors where the temperature is 92 degrees Fahrenheit. And after 1 minute, now the thermometer reads 81 degrees Fahrenheit. What is the reading after 2 minutes, and when will the thermometer read 90? Okay, the object that we're looking at that's changing temperature is the thermometer, okay? So this 70 degrees Fahrenheit represents the initial temperature of the thermometer. 92 degrees, that's the temperature outside. That's the temperature of the surroundings where that thermometer is. Not pleasant weather. So I know C is equal to T naught minus TS. So that's 70 minus 92, which is negative 22. Okay, so remember our model has the form T of T equals T sub S plus CE to the KT. So now I can write T of T equals 92 plus, or actually it's negative, so let me write minus 22e to the KT. So again, I need to find K, and that's why they told me right here, after 1 minute, the thermometer reads 81 degrees Fahrenheit. So that means I'm going to plug in 1 for little t, set the whole equation equal to 81, and find K. That's why they always give you that one little extra piece of info. So we've got 81 equals 92 minus 22e to the KT. So negative 11 equals negative 22e to the KT. I just subtracted 92. Now I'll divide by negative 22. So that's just going to give me 1/2 on the left-hand side. Oh, and I need to plug in 1 for t. Just having so much fun, I forgot to. Times 1. What a nice number to plug in. They really like us. So 1/2 equals e to the k. So k equals ln of 1/2, which is about negative 0.6931. So we can write our model now as T of t equals 92 minus 22e to the negative 0.6931t. Okay, I'm going to box that because we're going to use it for the other parts. And don't get all tripped up because they didn't break it into parts A, B, and C. They're still asking the same 3 things as the previous example. It's just not nicely chopped up for you. Okay, so now this is basically what part B was, right? What is the reading after 2 minutes? So you're going to plug in 2 for lowercase t, right? So after 2 minutes, they want t of 2. So that's going to be 92 minus 22e to the negative 0.6931 times 2. Okay, and just show the setup. If you're in my class, that's all I need, and then punch the rest in the calculator. So it's about 86.5 degrees Fahrenheit. Make sure you do put the units though. Degrees Fahrenheit matters. And then the last thing is, when will the thermometer read 90 degrees Fahrenheit? So when is it going to be 90 degrees Fahrenheit? Well, again, you're going to set this equal to 90 now. So 90 equals 92 minus 22e to the negative 0.6931 times t. We're solving for little t. What do we do first? Subtract 92. Good. So negative 2 equals negative 22e to the negative 0.6931 t. Divide by negative 22, so that's going to be 1 over 11 equals e to the negative 0.6931 t. And then take the natural log of both sides, so ln of 1 over 11 equals negative 0.6931 t. And then divide both sides by negative 0.6931, and you get t equals ln of 1 over 11 over negative 0.6931, which is about 3.5 minutes. So did you notice something? You didn't need calculus to solve any of these problems. We just used calculus to understand where the model came from and how these growth rates were in proportion to the initial amount. And that involved calculus ideas. But the actual problems themselves, you could have done back in pre-calculus. And in fact, I have a very similar video for my pre-calc classes. I'll link it here should you be interested to watch it. But it's essentially the same idea, just minus the background, because pre-calculus is really the precursor to this course. So that concludes the lesson. Hope you enjoyed it. When you study more calc, you'll go into exactly understanding more precise models and other ways that we can model population growth, bacteria growth, etc. It can get really interesting. So don't forget to give the video a thumbs up. Stay tuned. We've got more differentiation rules and fun for you coming up.